This converts it to a value in the ball. Because we're in the fourth direction, right? Yeah, it would make sense.
Yeah. It may just be that I'm tired, but there's something I'm missing. But it's something, let's just say, it's something close to this, if it's not.
Yeah.
So, oh yeah, go for it. Of course, this is the part that's not in the book. The converse direction, I think, is...
Yeah, the converse
is in the book, right? And so let's...
Sorry about that.
You're okay. I probably shouldn't have erased part of what I just erased. Oh well. All right, so sorry, I just lost your paper there. So if he says, okay, so he says, assume E is infinite dimensional. This marker. That's close, but no cigar. It's here. So actually, it was a swish, Audric. I made it perfectly. All right, let's see here. So suppose E is infinite dimensional, right? He says, using Ries's lemma, we construct a sequence x sub n. Construct sequence x sub n in E such that the norm of xn is equal to 1 for all n in n, and the norm of xm minus xn is greater than or equal to half for all m and n with m not equal to n. Does that make sense so far?
Using epsilon as a half.
So put epsilon equal to a half, and so this is in the unit ball. Now xm doesn't have to be in the unit ball, right? But the n is. So we don't. He didn't tell us where this was yet, did he? I guess it's also, yeah?
Yeah, from the lemma it would have to be.
Oh, it is, that's also in the unit ball. Right, yeah, because it's also, the n could be m, in short, yes. Okay, so he says let x1 be any element in E such that the norm of x1 is 1. Since the span of x1 is a closed proper subspace of E, there exists in x2 such that, all right, so consider x1 such that the norm of x1 equals to 1. Then you can basically take x equal to the span of x1, right? This is closed proper subspace of E, right? And what's the deal with x2? And there exists an x2 in E such that the norm of x2 is 1 and x1 minus x2. So there exists, right, x2 in E such that the norm of x2 equals to 1 and the norm of x2 minus x1 is greater than or equal to 1/2, right? think we're using Ries's lemma. I mean, we constructed this. So then what?
Quick question.
Yeah.
Probably another question. But we can say it's a closed proper subspace because we're assuming E is infinite dimensional. The proper element, is that right? Why we can say proper?
That's a good question. Why is it a proper subspace? Yeah, partly because you're right, exactly. If it wasn't a proper subspace, that would mean, if it was the whole of space, then the space is one-dimensional, right? So that, okay, so that's good point.
Yeah, sorry, no.
Maybe that's actually where the finite dimensional. Okay, so I've been wondering what breaks down about this for finite dimensions, right?
Oh, yeah.
And maybe that's exactly it. I should understand more critically the proof of Ries's lemma where we use the fact that it was a proper subspace.
Oh.
I don't know if I really remember exactly where we used that it was a proper subspace in the argument, you know? But okay, so we have this, and then what? Well, so suppose and then he's like, okay, so suppose you've already done it for x1 through xn. Then since the span of x1 through xn is closed in proper subspace of E, there exists, xn plus 1. Right? So he's like, likewise, you can do this for n, essentially. Likewise, if you've got, x is equal to the span of x1, x2, xn, then there exists xn plus 1 with the norm of xn plus 1 equal to 1, and the norm of, xk minus xn plus 1 greater than or equal to a half for all k from 1 to n. So then what? What good does that do us? All right. He says, okay, so suppose xn has a convergent subsequence x sub pn such that x sub pn goes to x for some x. So I think, let's see here. So what's going on is, so what we're doing is we're using Ries's lemma to build a particular, unending unending subspace of this infinite dimensional space, right? And with respect to this subspace, we're going to find a contradiction to the closed unit ball being compact, I believe, or something like that. Let's see here. So, suppose xn has convergent subsequence xpn such that xpn converges to x for some x in E. All right. Then what? 1/2 is less than or equal to the norm of xpn minus xpn plus 1, which is less than or equal to the norm of xpn minus x plus the norm of xpn plus 1 minus x for all n. Now, why is what I just wrote true?
Second, and why is triangle quad?
Well, yeah, okay, that one I understand. But
Is that just by construction, what we're just doing?
yeah, so it's, oh, right, I think it was greater than or equal to half, but the half goes under excuse me, the 1/2 is less than or equal to the norm. I'm an idiot. I just, if you write the half on the other side, the greater than becomes a less than. So yeah, sad but true. I need to understand that. And then, okay, great. So then that's just this. So by construction of the sequence, but then that's problematic because why? We're supposed to have that the norm of xpn, both of these are supposed to go to what for the convergent subsequence? Like, see this right here? This right here? This forces this and that to go to 0 as n goes to infinity. Those can't both go to 0 if they're above 1/2. So this is a contradiction. So this contradicts the convergence of the subsequence. And since this construction is like, what's it using? It's just, as you said, using the fact that it's always a proper subspace, right? Because Ries's lemma rests on it being a proper subspace. And if you try to do this thing, if you try to do this construction in finite dimensions, at some point you run out of proper subspaces. And so that's where this construction falls down in finite dimensions, and why the the closed unit ball in finite dimensions is compact, whereas the closed unit ball in infinite dimensions cannot hope to be compact because this happens. Because you can always build this subspace to contradict, which contradicts the compactness of the unit ball.
Using Ries's lemma.
Yeah, and if you really plumb the depths of what we did last time, the example we got confused on at the end of class, that is kind of just exactly this sort of thing, because 1t, like I think you can almost see the 1, the t squared, the t cubed, those playing the role of like the x1s, x2s, x3s here. I mean, these are connected ideas. I don't fully understand all this stuff yet, right? But I'm working on it. I'm working on it. I'm trying. So, all right. So, let me see where we are time-wise. I can't remember when I started today. You're fine. I try to give you guys like an hour. Let's see here. I got 15 minutes left then, give or take. And the video, this is weird. So like, I don't know how to fix the settings on this. It's high def today. It may be fuzzy, but it's fuzzy high def. So, because these, like the camera comes set up for high def. And so like I take my camera, I set it back to, did you already get a picture?
I'll get another one. I think I got a picture for it, but sorry. Yeah.
I'll let you get a picture, just in case Audric needs a picture. He can get it from you later or something if need be. Although I think, well, anyway. Okay, so Banach spaces. All right, I feel infinitely more at home talking about Banach spaces than what we're currently talking about, because personally, the last time I wrestled with the issues we're wrestling with right now really was grad school. Like, I had a course in functional analysis and all of this stuff came up there, right? And then for whatever reason, I just haven't really run into it again since then, and maybe I should have, maybe, but anyway. Okay, so there we go. Let me give you back your book. And so section 1.4 on Banach spaces, we start with what's a Cauchy sequence, right? So a Cauchy sequence is what? It's one for which the distance between elements in the tail of the sequence gets arbitrarily small. So definition, sequence xn in a normed linear space E is called Cauchy sequence if for every epsilon greater than 0, there exists M such that the norm of x sub m minus x sub n is less than epsilon for all mn greater than m. So he doesn't even, I mean, I guess m could be an integer, but I guess it doesn't have to be. I mean, it's obviously a positive real number, I suppose. So let's see here. Trying to think, there's another way to state this in terms of limits, which is kind of interesting. So, let me not do that. So we have a theorem following our equivalent. A, you got a Cauchy sequence. B, the norm of xpn minus the norm minus xqn goes to 0 as n goes to infinity for every pair of increasing sequences of positive integers. Pn and Qn. All right, and C. Maybe this is the one I was thinking of. Actually, C is the limit thing I was talking about. I think the norm of xp. Oh no, it actually is not. Well, no, not quite. So xpn minus xpn plus 1 minus xpn. The norm of that goes to 0 as n goes to infinity. Again, it's a increasing sequence of positive integers. That's still the case down here. Okay. All right. Let's see here. Every convergent sequence is Cauchy. Convergent implies Cauchy, right? Why is that? Same proof you saw before, right? So like, if the norm of xn minus x goes to 0, right? As n goes to infinity, then what? If you take the norm of xpn minus xqn, he says that's less than or equal to the norm of, well, he's showing this off, isn't he? Okay, so that would be basically add and subtract x, right? So you got your x, and then we use the property of the norm to absorb the minus as you want, right? Triangle inequality, this thing. But these are two subsequences. So we're assuming, of course, that Pn and Qn are increasing sequences of positive integers. So we're looking at two subsequential limits of the sequence, but we know that all subsequential limits of a convergence sequence likewise converge. So these are both going to a 0 as n goes to infinity, right? And as such, we get that. So by criteria B, we have a Cauchy sequence. Yeah. I don't know. Like, I mean, this is not bad, I guess. I guess he's just trying to show off the utility of part B. But there is a simpler proof for this, right? Like, because like the easier real analysis proof, which doesn't rely on all this, at least I don't remember doing this in real analysis. Maybe it was there, I don't know. Alternatively, if you just look at like, you know, the norm of xm minus xn, that's less than or equal to the norm of xm minus x plus the norm of, you know, xn minus x, right? And so because you have convergence, you can, you know, choose the maximum of the positive integers needed to make both of those as small as epsilon over 2. Consequently, that's less than epsilon over 2 plus epsilon over 2, which is less than epsilon, consequently Cauchy. So, you know, pick this. Well, I'll just leave it at that. This, you can do the epsilon x, but that's the key. Like, you can do that is a method of proof. Convergent implies Cauchy. All right, so what's up next? Well, space of polynomials. Let's see here. He's like example 1.43. I'm trying to get to that one you asked me about before class. That's what I want to get to. P of 0, 1. Space of polynomials on 0, 1, okay? With the norm of P, the max norm, right? So max on 0, 1. P of x, take the absolute value of that thing. All right. And he says define Pn of x equal to 1 plus x plus 1 over 2 factorial x squared plus 1 over n factorial xn. All right. He says this is a Cauchy sequence. This is a Cauchy sequence in this space of polynomials. But it does not converge to a polynomial. Right? The limit of this sequence, of course, you might recognize is the exponential function, right? So like this goes to e to the x as n goes to infinity, which of course is not a polynomial. The proof that that's Cauchy, right? What's it look like? So let m be greater than n without loss of generality. Then if we look at the norm, well, if we just look at Pn, forget about norms for a second, just look at Pn of x minus Pm of x minus Pn of x. What's that look like? Right. Okay, so you're like 1 over n plus 1, did you say? X to the m n plus 1, right? Da 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 dot plus 1 over m factorial x to the m, right? And so what is the norm of that? It's the max, so
it's just when each one.
yeah, I think it's just, yeah, it's just this, right?
Oh yeah, it's the factorial. Yeah. And then we can make that.
I guess right. So yeah, I mean, I guess it's technical, but for for any epsilon greater than 0, you can pick a big M such that M comma N makes that as small as you want. I mean, that seems reasonable. It also seems like a pain to work out directly. There's probably some like really like simple.
RB, like for any real number, like epsilon is an example that you do that.
Yeah, I feel like there's some way to recognize what you're doing as like the tail of a partial sum for the exponential. And then since you know that like partial sums for the exponential function converge, you can piggyback off that result to like make your life simpler. But goodness gracious, I don't want to do it right now. Okay, so let's go on. I just wanted to do enough to get into trouble there. Yeah?
That leads us, sorry real quick, that leads us to conclusion that if it's a Cauchy sequence, it doesn't necessarily converge.
Ah, yes, exactly. So not every Cauchy, thank you, good point. Not every Cauchy sequence converges. This apparently is a Cauchy sequence which does not converge inside the space. Now it does converge if we put this set of polynomials in a larger context, right? In the space of all continuous functions on 0, 1, well, the exponential is a continuous function on 0, 1, right?
Yeah.
So the exponential exists. It is, in fact, in C0, 1, but it's not in P0, 1. So polynomials are not what we call a complete space. So like lemma 1.44 is important. It says that if you have a Cauchy sequence in a norm space, then the sequence of norms converges. All right. So I'm not even going to write that down. I'll just say that's an important lemma. I'm sure we'll need to use it. And then we have the definition, right? The definition of Banach space. What's a Banach space? A normed linear space E is called complete. It's complete if every Cauchy sequence in E converges to element of E, right? A complete normed linear space is called a Banach space. And then the example you were asking me about, so we'll finish class with this. Let's just try to like understand. I mean, what are examples of Banach space? Well, there's tons of examples. We'll talk about those next time, right? But example 1.46 is he's claiming that L2 is complete. L2 is a Banach space. All right, so he says, let A sub n be a Cauchy sequence in L2. Now, L2, we had the norm, which was what? All right, well, let's see here. He says, so then given any epsilon, all right, so if A sub n is equal to alpha sub n comma 1 comma alpha sub n comma 2 comma dot 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 dot, then given any epsilon greater than 0, there exists and not such that the sum k equals 1 to infinity of the absolute value rather of alpha m comma k minus alpha n comma k squared is less than epsilon squared. Okay, so he's squaring this is the square of the 2 norm. That's why you've got epsilon squared. I mean, if you want, we could, there you go. That's direct application of the Cauchy criteria. Now, so you were asking about the double indices, right? And let's see here. So let's try to break it down. What's going on? The issue is the points in L2 are themselves sequences. So a sequence in L2 is a sequence of sequences.
Oh, yeah.
And that's why there's this double index.
So that's, yeah, sequence, exactly. Okay, that makes sense. Yeah.
So like, so for a fixed n here, that's a sequence of real numbers, right?
Well, sequences in, there's a sequence of sequences in L2.
Yeah, my point is like if I put n equals 1 here, that corresponds to the sequence alpha 1 1 comma alpha 1 2 comma alpha 1 3. 1 is fixed forever and ever, right? If I look at A2, it's the sequence which is A2 1 comma alpha 2 2 comma alpha 2 3. Da 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 da. So that's the notation that's going on here.
And that makes sense for the question.
Yeah.
Okay. Thank you so much. Yeah.
So that's it, and we'll sort through all that next time because I think I'm out of time, but probably, yeah. So, sorry, I have spent far too long on the Reese's lemma thing, and I still don't think I've brought the clarity I'd like to it.